All right, so last time we were talking about the second problem in Big Bang theory, and that is the horizon problem. If I called that the flatness problem, that is the first one. My bad. The second one is the horizon problem. So the horizon problem stems from the fact that the cosmic microwave background, which is what this is, CMB for short, is overall very even. So a reminder is that this oval looking thing over here is actually a temperature map. So spots where you see red spots here, that's really hot temperature, and spots where it's overall really dark, that's colder. So this is it's called a heat map because it literally shows you where it's hot and where it's cold. And of course, like we don't measure an oval. This is like measuring the entire night sky in every single direction and then putting it on a flat surface, the same way you do for the planet for Earth, for example. If you can't make a map on Earth on a flat surface, obviously, because Earth is round, it's a sphere, and you can't really project that very well into a flat plane. So you make what's called a Mercator map, which is like the familiar picture of the globe that you see on a flat surface. So this is the same idea. So just to make sure, this thing here is measured over a entire sphere of the night sky in every single direction. And if you can wrap this around back into that sphere, it would basically look like a little mini globe. And so anyway, you have a heat map here, the cosmic microwave background. We call it microwave because these photons which are emitted really, really, really early in the universe's history, they get redshifted all the way to the microwave background. So back then, they were photons of much higher energy. Today, they're much, much lower energy. They get redshifted to the microwave region. But the horizon problem, it stems from the CMB and how flat the CMB is, or how even the CMB is in temperature. So it doesn't look like it's very even. If you look at this, it looks like the red spots are really red, the blue spots are really blue, so there's different colors, there are different temperatures everywhere. But actually, the scale of this is small. It's 10 to the power minus 6. And what that means is that the really bright spots and the really cold spots, so like these two regions over here, are separated by only 10 to the power of minus 6 Kelvin, which is the unit of temperature, right? So that's 10 to the power minus 6 Kelvin between the bright spots and the dark spots. So the temperature here, the brightest of the bright spots that you see on the CMB and the bluest of the blue spots that you see on the CMB are only separated by a temperature of 0.000001 Kelvin. So what that means is that the CMB is really even in temperature. So that means if you point your telescope up, if you point your telescope down, left, right, whatever angle you want to point your telescope to, the temperature in the sky is all, or the temperature of the photons which are coming in that direction are all the same temperature. Okay, so it's remarkably even. It's actually really bizarrely even. So if you are the experimenters of this, the ones who actually got the CMB, so they launched a probe and they put that in space. It's called the Planck satellite, if you've ever heard of it, after Max Planck. And the satellite that orbits the Earth that actually made these measurements, no matter what direction it pointed its sensors at, basically the temperature of the photons which are hitting the satellite are the same in every single direction. That's fine. As a reminder, these photons, where are they coming from? They're not coming from stars, they're not coming from the galaxy. These are the photons which were emitted all the way early on in the universe when, in my last video, when I described the fact that there was a time before atoms existed, then the universe got cold enough, and then atoms did exist, but they were overall ionized. The protons and the electrons weren't able to come together to make hydrogen yet, because it was still too hot. But the universe expanded, temperature dropped, and then eventually the universe was cold enough for the ionized particles to come together to make hydrogen, helium, and all the other atoms. When that happened, the photons, which are just going around, bumping into particles at the time, could no longer go around and bump into particles. Because unless the photon has the perfect amount of energy to be absorbed by a hydrogen atom or a helium atom, it doesn't. right? As you know from NYC, it doesn't have exactly 13.6 eV. It can't make the transition from N1 to N2 energy state for the hydrogen atom. And the photons in the early universe did not have exactly 13.6 eV of energy. And so when the protons and the electrons came together in the early universe to make neutral atoms, those photons could no longer be absorbed by anything because they were the wrong energy for the very, very early universe. They were actually much higher energy, and they couldn't be absorbed by the hydrogen. And that means those photons just went straight through. They kept propagating, they kept traveling, and in some cases they were absorbed, some cases they hit other stars, in some cases they hit other galaxies. But the universe is a big, empty, well, on big scales, the universe is actually quite empty. And so most of those photons don't hit anything, and they just keep traveling and traveling and traveling forever. And eventually, those photons actually make it to us. And they bump, if we're lucky enough, they bump into us. They bump into the Planck satellite, and the Planck satellite takes their measurements, takes their temperature. And that's exactly what we're looking at here. We're looking at those primordial, those really, really old photons, which are hitting the Planck satellite, which we're lucky enough to hit the Planck satellite. So this is the temperature map, and it's really even. It's strangely even, as I said, 10 to the power minus 6 Kelvin between the hot spots and the cold spots. And that shouldn't be the case. I mean, if you really think about it, like these photons coming from every direction from the very early universe, there should be some variability there. Like you'd almost expect that certain directions to be hotter, other directions to be colder, but you certainly wouldn't expect that every single direction would have exactly the same amount of temperature. Why not? That's what the horizon problem is. But why wouldn't we expect every direction to have the same temperature? There's a very good reason for that. And before I get into it, let me tell you what temperature is, right? So if I had a room, and for the sake of this argument, my room will be a box. The temperature of the room, well, obviously this room is going to be filled with a whole bunch of stuff, right? So there's air inside of this room, oxygen, whatever. These are atoms. Okay, so these little green things here are going to be the atoms inside the room. Those could be anything. It could be air, whatever. But what temperature actually is actually just the kinetic energy. These atoms over here are obviously moving around. They're bouncing back and forth. So these atoms are actually going to hit that wall. They're bouncing around. This atom will move here, hit the wall, bounce back, and it'll be a mess. The atoms are, zooming everywhere, hitting everything. And they all have kinetic energy. And as they hit other objects, they deposit a little bit of that kinetic energy onto that object they hit. Could be the walls, could be you, could be a thermometer. And the thermometer would measure the amount of kinetic energy that the atoms are moving with, that are hitting them with. And the amount of energy transferred to it is basically a really, really rough estimate of how temperature is measured. Right? So temperature of those atoms or those particles is proportional to the amount of kinetic energy they have, actually. Okay? So what's important for you to understand here is that temperature is related to the kinetic energy of objects. And the kinetic energy requires that in order to measure temperature and actually measure what the kinetic energy is, you need that object to hit you. You need that object to actually get to you. So what do I mean by that? If I take a room, let's say I make this a little bit of a larger room, and if I put a hot cake inside that room, so here you have a table, and you place a cake on top of the table, and then there's somebody else inside the room. What'll happen, obviously, if the cake is really hot, so let's say we made the cake, 300 Kelvin, and we made the other person, I don't know what the temperature of a human body is, but say 250 Kelvin or something. There's a 50 Kelvin difference between them. If I waited long enough, if I waited some amount of time, eventually both of these objects, the cake and the person, are going to have the same temperature. Eventually. So eventually, if I waited long enough, I don't know what that equilibrium temperature would be. Let's say they both end up at, 298. whatever it is, they both come to the same temperature in equilibrium at some point. How does that happen? So, because temperature is basically just the manifestation of kinetic energy, what needs to happen are that, the atoms which make up this room need to bounce onto the cake, get some kinetic energy from the cake, and begin bouncing back to the person, deposit a little bit of that kinetic energy to the person, and you need this process to happen millions of times, tons of times, such that they keep communicating, they keep going back, atoms keep going back and forth, taking energy, depositing energy, removing, adding, until they're both exactly at the same equilibrium energy or equilibrium temperature. But you need atoms to go back and forth. You need them, the particles or the air or whatever it is of the room, to actually go back and forth between the cake and the person in order to match temperatures eventually, in order for them to come to an equilibrium. So that means there needs to be enough atoms to actually make the trip, or enough air particles to make the trip between the two people to bring you at a thermal equilibrium. So what I'm getting at over here is that in order for temperature to be at an equilibrium, to be very even, like it is at the CMB, you need to have those air particles actually go back and forth and communicate enough such that they could eventually come to an equilibrium in terms of their kinetic energy. They need to make the trip. They have to physically go back and forth. But what if I made my room really large? What if, instead of my room being a regular room, what if I made my room a box? And this box is 1 million. So 1 times 10 to the power of 6 light years. And once again, I take my cake, place it here, and on the complete other end of the room, I'm going to put my person. Well, this is 10 million light years, right? So in a single year, light will travel a light year. So this will take me 1 million years, at least if my particles are moving at the speed of light, 1 million years to get from the cake to the person, right? So that means if I take my boiling hot cake, if I take my cake and let's say I make this 350 Kelvin, and I take my person here, and this person's still 250 Kelvin, if I waited long enough, they will come to the same temperature. They have to, because there's thermal equilibrium. But the process by which that will happen, is for the atoms, or whatever it is that makes up this box, this room, will have to go back and forth. We'll have to take some kinetic energy from the cake, make the trip to the person, and they need to transfer some of that energy, some of that kinetic energy. And then this needs to happen millions and millions and millions of times for the temperature of both people to come to a thermal equilibrium, for them to both have the same temperature. But wait, this box is 1 million light years. So the time it takes for that to happen is just one round trip is going to take 2 million years. It's got to go, which is going to be 1 million years, and it's got to come back, which is going to be 1 million years. So a single round trip is going to take 2 million years. And so if I asked you after 10 minutes of this, are they in thermal equilibrium yet after 10 minutes? Well, most definitely not. There hasn't been enough time for particles to go from the cake to the person yet. What about in 100 years? Still not enough time. 1,000 years, still not enough time. 100,000 years, still not enough time. After 1 million years, there's enough time. But they got to come all the way back to recommunicate. They have to come all the way back to redeposit some of that kinetic energy to the cake. And there's simply, in 1 million years or in 100 years, there's not enough time for that to happen, right? There's going to be a certain amount of time required to come into thermal equilibrium. That is what the horizon problem is. If you took the distance of the photons which are emitted here and over here, and if you were to calculate how far apart those photons are in the early universe compared to today, you'd find out that the distance that separates them is actually more distance than there was enough time for the photons to go back and forth. Which means this is almost like the example of the cake and the person being too far apart to be at the same temperature. In other words, what I'm saying is that there's too much space in between here and there for those photons to have made enough round trips to be at the same temperature. In fact, it's not even a question of enough round trips. There hasn't been enough time for them to make even one trip. The distance between these two spots, as we're going to calculate, this is called the horizon distance. And basically, what this means is that there's going to be more space. There's way more space than we think in the universe. And there hasn't been enough time for photons to actually make the trip from one end to the other end. And so if we're measuring photons coming from two complete opposite ends of the universe in the CMB, they better not all have the same temperature, because there's no way they could come to a thermal equilibrium with a volume of space that's that large. And yet, that's exactly what we see. Exactly what we see is that although the universe is gigantic, and even though the universe is only 14 billion years old, 14 billion years old is not enough time for the photons on one end of the universe to make it to the other end, because the universe is larger than that. And so those two ends of the universe better not be at the same equilibrium temperature. And yet they are. In fact, everywhere in the universe is at the same equilibrium temperature, even though the amount of space that separates all these points is way too far for the photons to have made enough round trips to come to a thermal equilibrium. And that's why we called it the horizon problem. The CMB should not be equal in temperature everywhere, and yet it is. And we can calculate this, actually.